Interesting. That escalated quickly. All right. So this is where we were yesterday. We said that we had the position of the particle is represented by s of t. We said the velocity is the first derivative. We said the acceleration is the second derivative. We asked the question, how do we know when the particle is not moving? And we decided that would be when the velocity is 0 exactly. Okay, so I'm going to add that to my notes. The particle is not moving. Okay. So what we've done now is we have made ourselves a number line. And we have numbers -1 and 9. Those are the two ends of the interval. And then we have 2, where the velocity equals 0, and 6, where the velocity equals 0. And now we're going to try to decide when the particle is moving to the left and when the particle is moving to the right. Okay, so I'm going to put a circle on 2 because at 2 the particle is not moving at all, so I'm not going to include that number. I'm going to put a circle on 6. At 6 the particle is not moving at all, so I am not going to include that number in my answer. -1 can be included because with -1 they put a bracket, and with 9 they put a bracket. So I'm going to put circles on those as well, but I'm going to fill them in because those are numbers that are going to be used. Okay, so what I need to do now is I need to pick a number that's between -1 and 2. What is a number that falls between those? 1. Okay, so I'm using the number 1. Oh, look at that. What color did you think that was?
Orange.
Pink. Interesting. Yeah, it's pink. It's pink. True story. See, pink? But it wrote blue. All right, so we have 3. What is 1 minus 6? -5. Okay, so we have a positive times a negative. What's 1 minus 2? Negative. So we have a positive times a negative times a negative. That's a positive. So I'm going to put a plus right up here. I don't care what the number is. I just care that the sign of the number is positive. All right, what's a number between 2 and 6? 4. Okay, so that's positive. 4 minus 6 is negative. 4 minus 2 is positive. So I have a positive, a negative, a positive. So overall, that's negative. A number between 6 and 9, 8. So I have a positive, a positive, a positive, 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 positive. We are positive. All right, so based on those answers we just got, we're going to say that the particle is moving to the right from -1 to 2 in that time frame. It is moving to the left from 2 to 6, and it is moving to the right from 6 to 9. And the reason I know that is because the particle is moving on the x-axis typically, and so positive means right, negative means left. Okay, so I'm going to go ahead and say moving right. And we'll say from -1 to 2. Why do I put the U there? Yeah, it's 2 different answers. I have to use both of them. So the U tells me one and the other. It means union, one and the other at the same time. Moving left is from 2 to 6. Thank you. Appreciate that.
My G's look like S's. Yeah.
Yeah, that's fair.
I kind of write them kind of a little bit cursive. My handwriting is like a kind of weird mix of some bits of cursive and then.
All right. So next, we want to see when the speed is constant. So how could you know when the speed is constant? When acceleration is 0. Okay, so the next thing we're going to put on our notes, I'm going to keep this up here so we can still see it. we're going to find where acceleration is 0 because this means that the speed is constant. So my acceleration function was 6t minus 24. So I'm going to say 6t minus 24 equals 0. And you can factor to solve this if you want, or you can just move everything away from t. It doesn't matter. Works both ways. So do you guys want to move stuff away from t, or do you want to factor? Factor. Okay. I kind of like the factoring idea because I think it makes it easier to plug numbers in for your sign chart. So this part right here, this right here, I call this sign chart, okay? Because we're figuring out what signs we have. So, nope, not a sine as in a sine curve. I always know that I'm doing a good job teaching when people start making math jokes, and that, my friend, was a math joke. All right, so what is the time when the speed is constant? 4 seconds. Okay, so what we're going to do is we're going to see when the speed is accelerating or decelerating, okay? So we're going to make a number line again. We're going to go from -1 to 9, and then what are we going to put in the middle? 4. And it does not equal 4 because that is the one moment where the speed is constant. And then here we can include those because we had brackets. Notice I did not use the words speeding up and slowing down because what do speeding up and slowing down refer to? Not acceleration. Velocity, right? So so when we talk about speeding up and slowing down, we're going to look at the v of t and the a of t at the same time. We're going to look at both of them. So that's why I'm not calling this accelerate or speeding up and slowing down. I'm going to specifically mention the words in terms of acceleration. So accelerating, decelerating. Okay? Yes. Two. Was I not sure in the video?
Yeah, and then you put 1.
Oh, I don't know. You're right, I did. Accelerate has 2, but does decelerate
Yes.
have 2? 1?
Sure. Well, I can't be so I can just go.
So the beautiful part is that in my notes I only put 1, so maybe I spelled it right. Also, I'm a decent speller because I'm a math teacher who likes to read. So I typically spell things well.
It's nice and yeah. They only have 1 C.
Decelerate is 1 C?
It's decelerate.
Yeah, let the records show that Miss Rice spelled decelerate correctly last year. So that's marvelous. Thank you, thank you, thank you. Stephen and I were very invested to know that. All right, so pick a number between -1 and 4. 2. And then we plug it in. So we have a positive, and then 2 minus 4 is a negative, so positive times negative, negative. And then a number between 4 and 9? 6, all right. Plug it in, we've got a positive times a positive. Okay, so our conclusion is that we are decelerating with 1 C, because we know how to spell it, from -1 to 4. And we are accelerating from 4 to 9. Yes. Yes, it is. All right. What we're what we're going to do next. You guys make me so proud sometimes. What we are going to do next is we are going to test to see when the particle is speeding up versus slowing down. So what we're going to do is we're going to draw another number line, and we are going to combine the v of t with the a of t. Okay, so the signs that we had for the v of t sign chart and the signs that we had for the a of t sign chart, so that we can see how they compare with their signs. So if you guys can see, I'm doing the 2, the 4, and the 6 all at the same time. You notice that? Okay. I'm going to go ahead and put v of t on the top. We're going to see if it was, because we're going to compare we're going to compare both signs together. So if I look at v of t, I'm just looking at that first sign chart we did. We said it was a plus from -1 to 2, and then from 2 to 6 it was a minus, and then from 6 to 9 it was a plus. So all I did is I took my signs from up here, and I copied them and I put them down here. And now I'm going to go ahead and take the signs from my a of t, and I'm going to plug those in. So from -1 to 4, I have a negative, and from 4 to 9, I have a positive. Okay. So how do we know when it's speeding up? How do we know when it's slowing down? Yes.
When the signs are the same, that means it's speeding up.
Okay.
Even if you're both negative, it's giving the appearance of it.
Yes, the particle would appear to be speeding up. So, yep, and then if they're different, then it's slowing down. So we have two places where we are speeding up. So what should I write for speeding up?
Well, parentheses 2, 4.
Yep.
Parentheses union, parentheses 6, 9 bracket.
Yes. Okay. And then for slowing down, what should we put? Okay. Okay. Mm-hmm. Okay, so the next thing we talk about typically with particles is the difference between total distance traveled and displacement, okay? So we're going to calculate the total distance, and we are also going to calculate the displacement. Okay, so I live about 10 miles from school. So what is my total distance that I drive every day? 20 miles. We don't say positive 10 to school, negative 10 back home, I went 0 miles, right? That'd be weird. We say I went 10 miles one direction, 10 miles the other direction, altogether that was 20. Does that make sense? When I am at school, my displacement from home is 10 miles. When I am on my way to school and I've only traveled 2 miles, then I would say my displacement is 2 miles. When I'm on my way home and I've traveled 3 miles, I would say my displacement is 7 miles. Does that make sense? So what does displacement mean? It's how far you are from the start, okay? So when we calculate, yes, sir. Oh, the quiz. Hang on, pause your thinking. Let me pause the video. Okay, so for displacement, we're going to remember, this is kind of like the formula, but it's very easy. We're going to say end minus beginning. So where you ended up minus where you began, that's how far you are away from where you began. That's your displacement. Yes, because that's how far from home I was. Mm-hmm. Yes?
If you're beginning somewhere and you're subtracting that from the endpoint in which you are, no matter what, that's going to be your total distance. It can't be negative.
We're going to talk about total distance, and then I think you'll see where the absolute value kind of comes in. Yeah. All right, so total distance, this is where I was talking about we don't have negative values, right? Because if I was counting this, I would say I drove 10 miles to school, and then I drove 10 miles home, so that's like a positive 10 plus a negative 10 equals 0. That's where the absolute value comes in, because I don't want to zero out my total distance. I want to say that I traveled 20 miles total. So what we do here is we take our t values, and we want to use t values that are the end points of our interval. And then we also want to consider the t values where we stopped moving, because that's where we switched directions. Okay, so what t values am I going to use? I'm using the end points, and I'm using the t-values where I stopped moving. So -1, 2, 6, 9. So -1 and 9 are the endpoints, 2 and 6 are the moments where I stopped moving. All right, so those are the moments where I switch directions, and so that's where I want to say, okay, even if this number is negative, I want it to be positive because I want to add up these total distances. All right, so t is our first. This is going to be kind of like a chart. S of t is going to be the position we are at. So what do you get when you plug -1 into S of t? So this could be the calculator part if you want. So -1, -12, -36, -20. It's -61. 69, thank you. All right, so when the particle started moving, that was its position. So that's where it started. That's our initial value. All right, what do you get when you take the position function and you plug in 2? -48 plus 72 minus 20. Y'all have calculators in front of you? Type. It's 12. Okay, when you went from a position of -69 to a position of 12, how far did you travel? Stop ruining it for them. 81. Okay, so we're not adding the distances together, right? We're finding the difference between them. Okay, so if you want to think of it as I did 12 minus -69 and got 81, you could think of it that way. If you wanted to think of it as I took the absolute value of 69 and added it to 12, you could think of it that way. The important thing is that the difference between those, or the space between those, is 81. Okay, what about when we plug in 6? So we want to know where the particle is at the time 6. And yes, it is possible that they would give you an FRQ where you had to do this by hand, no calculator. It's annoying. I would not be surprised. Yeah, but you do it. You do it.
I'll do it. I'll draw sad
Yeah.
face.
It's -20. So how far is it from 12 to -20? 32. Okay, and then what happens when you plug in 9? Go for it. Go for it. Yeah. No one's allowed to say it out loud, especially Stephen. Sorry, Stephen. No, they don't. You can doodle on there. They will not grade it.
What if I like write them a message, staple a $20 bill to it?
Yeah, you can communicate with them. It's the same as like if you were to write a note to me on a test, it's not going to make a difference. But I might smile when I see it. Yeah.
Yeah. Probably find dudes already.
This is a great use of time right now.
Because it's fun, that's why. We would say that.
Hey guys, what color is my water bottle?
I can't tell what color it is normally, so. I can't tell. I can tell the bottom part is, but the top is blue or purple.
Right away.
I think I'm gonna go.
Oh, 369, 349? 349?
It is not.
Oh.
Wait. I'm almost done.
Is it 61?
It's 61.
All right, so the difference between these two locations is what? 81. So if we want to calculate the total distance, we're just going to add those three numbers up. And so the total distance traveled was 194. If we want to know the total displacement, so if we say that the starting position was negative 69 and the ending position was 61, then we're going to do 61 minus negative 69. And so what's the displacement? So when the particle got to the end of the interval, it was 130 units away from where it was when it started. That's what displacement means. But to get those 130 units away from where it started, it did a little bit of back and forth movement, and so it actually traveled 194 units while it was doing that. Does that make sense, the difference between displacement and total distance?
So what I did
All right.
wrong was I put a negative.
All right. So
misread my 9 as a 7. That's
you would be surprised how many times that happens. Okay, so it says, suppose Joshua drops a ball off the observation deck of the CNN, I think it's supposed to be CNN tower. It's 450 meters above the ground. If the distance in meters fallen after t seconds is given by this equation. It says, find the speed of the ball after 5 seconds. So if you look at your blue sheet, how do we find speed?
We derive it.
Absolute value of the first derivative, v of t. Okay, so I'm going to say if y equals negative 4.9 t squared plus 450, then what is my first derivative? T. Okay, so we're going to say y prime of 5, and we're going to put that in absolute value, right? So this is the position equation. This is the velocity equation. This is saying the absolute value of velocity. Absolute value of velocity. Because velocity is a speed with a direction. So when you want just the speed, then you take away the direction. So we're going to say it's the absolute value of negative 9.8 times 5. And you can go ahead and use a calculator if you want. What do you get? But you get 49. So we're going to say 49. And then what should the units be for speed? Meters per second. Okay, so that was part A. Part B says find the speed of the ball when it hits the ground. So think about which equation is going to tell us when the ball hits the ground. Yeah, so we would say the original equation, the position equation, has to equal 0 because the position equation tells us its position. When it's on the ground, that would be 0. Okay, so we're going to say we're taking the equation y equals negative 4.9 t squared plus 450, and we're setting that equal to 0, and we're solving for t. So what do I need to do? Minus the 450. And then divide by the negative 4.9. So I'm going to get t squared is 450 divided by 4.9. It was negative over a negative, so I just got rid of my negatives. Okay, and then how do I solve for t? And whenever I square root, how many answers do I get? 2. So I'm going to say t is, I'm going to go ahead and put an equal sign, plus minus, and I'm just going to leave this as that number so that I have an exact answer right here. And what am I doing now with that number to find the speed of the ball when it hits the ground? I'm going to plug that into the velocity equation, which is the first derivative, And I'm going to make sure I take the absolute value of it because I don't care the direction, I just care the speed. So I'm going to say y prime of that crazy square root. And I'm going to go ahead and do the positive version. Why am I doing the positive version? Because negative time doesn't really make sense in this situation. Yeah. So I'm doing the positive square root of that.
Negative time would end up giving you something when you climbing the stairs.
Right, right. Yep. So if we plug that in,
Aren't there still two scenarios here for the plus or minus? The square root?
it doesn't make sense in the context of the problem to have the minus side. That's like what Wolf was saying, is that would be like when he was climbing the stairs to get up there.
No, it's still the absolute value.
Does
Does it
Yep.
just not matter in this instance?
In this instance, it doesn't matter because we would say the negative time would be outside the domain of the problem. So 93.915 meters per second. All right, C says how far the ball must have already fallen by the time it is traveling. Find how far the ball must have already fallen by the time it is traveling 50 meters per second. This would be calculator active, probably. Yeah.
I mean, how are we going to do absolute value of the square root of 450 over 4.9 times?
Right. Yeah, that's calculator.
I mean, you could, it would be
About the square root of 10.
All right, so back to the problem we're doing. What do we need to do? Yeah, so we're going to say 50 equals the absolute value of negative 9.8 times t. So we're going to divide by 9.8. And then what does t equal? Actually, let's go ahead and call it just 50 over 9.8 because then it's easier to plug in than decimals. Okay, so where am I going to plug that back in? The original equation, because I want to see its position at that moment in time. So I'm going to say y of 50 over 9.8 is negative 9.8 times 50 over 9.8 squared plus 450. Say it again. Oh, 4.9. Sorry. Yep, you're right. So what do we get? Okay. So that's its position. How do we figure out how much it's fallen?
Minus that from 450.
Minus that from 450. So we plugged in that exact time to see the position that it's at. But the question was asking how far had it fallen at that time. So if that's the position that it's at, then 450 minus 322.449 gives you 127. So 127.551 meters is how far it had fallen. We subtract it from the beginning height, because if that was the position that it was at, then the beginning height minus that would be how far it had gone. Yeah. 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 What is the acceleration of the ball at any given moment, and explain why this is the case. So what do we need to do? So we have the original, yeah, we have the original, the position equation, the velocity equation. The acceleration is negative 9.8 because that is gravity. Yep. Because gravity.
Make
Okay.
sure gravity is in all caps and really big. Because gravity.
So, hey guys, I need you to listen. So when we talk about the position, the x-coordinate is in terms of seconds. The y-coordinate is in terms of meters, right? So if you think about the first derivative, your x-coordinate is still in terms of seconds, but your y-coordinate is the rate of change, and what would the rate of change be? Meters per second. So for the first derivative, we have seconds, and then meters per second for our units. And so for our second derivative, we have seconds for our x-coordinate, but if we do our slope here, we have y divided by x, which would be what? Meters per second squared. So gravity would be negative 9.8 meters per second squared. So the way that we find our units is we just think old school slope, rise over run. Just do your y-coordinate divided by your x-coordinate, and that will always give you your units. So the original equation was seconds in meters. And so if we're keeping the same x value as seconds, then the way that I go from here to here is I say, okay, the slope would be meters per second. And that's what got me to meters per second. And then when I went from here to here, I kept the seconds the same, but then for this unit, I did meters per second, which is how I got meters per second squared.
For which one did you get to meters per second?
For going from first derivative to second derivative, because the slope going from here to here would be the rise over run. And so it'd be meters per second over second, which is why we got meters per second squared. Okay. All right, so when you look at this packet, you're going to have a mixture of problems. A lot of them are going to have to do with particle motion, but some of them are going to be things like that, where you're dealing with not just particle motion, but like motion in general. Okay, motion of like a ball or whatever. So, yeah, that's fine. Yeah, that's fine. You guys didn't want to do that problem twice? You weren't feeling that? Strange. All right.